Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over kinetics, focusing on reaction rates and stoichiometry. So in my last video I ended with talking about the average rate of change and how that can differ depending on what points or what you're comparing in your data. In this video, I'm going to talk more about that, but I'm going to relate that to stoichiometry and how those reaction rates or the expression of those reaction rates can change depending on what substance you're looking at in your balanced equation. So let's get into this. So here I have an example of a balanced equation. I have C4H9 Cl reacting with water and is producing C4H9OH plus HCl. So all of this is a one-to-one ratio. So you'll see that this substance and water and this substance and HCl are all one to one to one. So when we're focusing on, say, C4H9Cl and C4H9OH, when we focus on these two, the reactant and product, it's a one-to-one ratio. So that means that for every mole of the C4H9Cl that is lost, you get 1 mole of C4H9OH created. So when we're looking at the reaction rates, then that means that the rate of disappearance of our reactant, C4H9Cl, is going to be the same as the rate of the appearance of our C4H9OH, which is a product. So these are directly related. So if we relate this to the equation, right? So the reaction rate is going to be equal to the negative of the change of the reactant over the change in time, which is also going to be equal to the positive rate of increase, right? So this is increasing over time. The change in the concentration of C4H9OH, the product, over the same amount of time. So these are going to be equal but opposite to each other. So the reaction rate is related to this expression here with regard to the reactant disappearing over time, but is also equal to the change in the concentration of the product, which is increasing over the same period of time. But then the question is, like, what if the coefficients are not 1 to 1? What if the ratio is like 1 to 2 or 3 to 6 or 2 to 5 or something like that? How do we do it then? Well, stay tuned and I will start on that right this minute. Okay, so what if the ratio is not 1 to 1? What if you have an equation that has different exponents, or I'm sorry, different coefficients, right? So here's an example. Let's go over another example. Here we have hydrogen plus iodine reacting to form HI, hydrogen iodide, or iodic acid, whichever form you want to take. Um, so for every mole of H2 here, we see that 2 moles of HI are produced. So it's not 1 to 1. So we're producing double the amount of HI compared to hydrogen being removed, right? So, or another way to think about it is you have half the amount of H2 that is disappearing compared to that of the appearance of HI. So the rate of disappearance of H2, the rate of disappearance of H2 is going to be half the rate of the appearance of HI. HI is being produced at double the rate that which you are removing H2 from the system, from your solution. So if you want to set them equal to each other, then what you need to do is you need to divide the HI expression by 2, right? So what you're always going to be doing, so if you notice, we have H2. So if this was a 3, then you would divide by 3, because then the loss of H2 would be 1/3 that of the production of HI. But we have a 2 here. So what you're going to notice is that in order to get them equal to each other, if you want to get the expressions equal, then you're going to have to divide that expression by its coefficient. So don't multiply by the coefficients. You're going to divide them to get them equal. So remember also that reactants are negative. So the reaction rate based upon your reactant is going to be, or loss of reactant is going to be negative because you're losing reactant. The concentration is decreasing. So the rate of the reaction will be equal to the negative of the change in your concentration of H plus over time, is going to be equal to half the rate of the increase, or the change in HI, which is going to be increasing because we have a plus sign here and it's a product over the same amount of time. So then in order to get these reaction expressions equal, so that they both express the same rate of the reaction, you're going to have to make sure you divide by the coefficients. And so here we have 1/2 because the coefficient is 2. And so that is how you express the reaction rate for a reaction based upon different reactants and products that have different ratios or coefficients. Let's go ahead and look at another example. Okay, so here's another example. So here we have our new reaction, which we have nitrogen reacting with hydrogen to form ammonia. So here we have 1 mole of nitrogen requires 3 moles of hydrogen in order to create 2 moles of NH3 ammonia. And so if we were to write out the reaction expression for this, we could write it out for each of the reactants or the product. And to make sure that all of the expressions that we get for the reactants and products are equal to each other and that those are all equal to the rate of the reaction, then we have to divide by the coefficients, because if we notice here that the rate at which nitrogen is disappearing or being used up or reacting is 1/3 that of hydrogen being used up, right? Or hydrogen is 3 times being used up 3 times faster than that of nitrogen. So in order to express both of those so that they both represent the rate of the reaction, we have to divide the rate of the expression for the rate of the disappearance of hydrogen over time by 1/3, so that that will be equal to the rate of nitrogen that is also disappearing, right? And so also we need to divide this by 2, so that way that uh, the rate of the production of ammonia is equal to that of the disappearance of nitrogen as well. And so here we have the expression, so it's negative. So the rate of the reaction is going to be negative the disappearance or change in the N2 concentration over time, and that's going to be equal to negative 1/3 of the concentration, the change in concentration of H2 over time, and that's going to be equal to the positive change in the production of NH3 concentration over time divided by 1/2 here. And so all 3 of these expressions are equal to each other and they equal the rate of the reaction. So this entire thing is the rate expression of the rate of the reaction. Okay, so the thing to keep in mind here is that these negatives are representing decrease and the positive representing increase. Now, when you get the change in the concentration of N2 or the change in the concentration of H2, those are going to be negative values. And those negative values are going to cancel out the negatives here. So you will get a positive rate of the reaction. So the negatives are going to cancel out. The negatives are going to take care of themselves. So you don't have to worry about that. You'll always get a positive rate of your reaction. So here is the generic rate expression. So here, I wrote a generic equation. So little a, little b, little c, and little d are the coefficients. So small letters are the coefficients, and the big letters or capital letters are representing the species that is overgoing the reactants. So your reactants and products. So if we're going to write the generic equation, rate equation for this, or rate expression for this reaction, it would be the rate is equal to the negative of 1 over A, little a, multiplied by the change in the concentration of big A over T, which is equal to the negative of 1 little b over little b, multiplied by the change in the concentration of big B over time, the change in time. And we have the ratio, or I'm sorry, the plus positive 1 over little c multiplied by the change in concentration of big C over time, which is also equal to the positive 1 over little d multiplied by the concentration, the change in concentration over time. And so if you want to express your if you want to express it correctly, then you have to multiply by the reciprocal of your coefficient. So you got to divide by, basically you're dividing by the coefficient in the expression. And so this is what you have for generic reaction rate expression. And so again, here I have written reactants decrease, so therefore it's going to be negative rate. So that's why you have the negatives there. And then products are increasing over time, so you should have a positive value. So these are going to be positive and these are going to be negative. Okay, so that's it for this video. In my next video, I'm going to go over some example problems using reaction rates and stoichiometry. If you enjoyed this video, if this was something you enjoyed and you learned from it, then please, by all means, subscribe to my channel, hit that notification bell. Also, like this channel, hit that like button down there, share this video with your friends. When you hit that notification bell, make sure you hit all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Oops. Yes, put a comment down in the comment section below. Let me know what you think. Ask me questions if you got them. I'd love to hear from you. Thanks for joining me. Have a great day.